We're really happy to have an in-person talk here in the Old Lodge in the Physics Department. So we're joined today by Dr. Horta Darrington, who is a Marie Curie Research Fellow up at the University of Edinburgh. And today he's talking about foundation models for astronomy. So without further ado, feel free to take over, Danny.
Thank you, Alex. Hello, everybody. People online, if you can't hear me, just tell Alex and he'll tell me to speak up. First and foremost, thanks, Alex, for inviting us to be down here. It's great to be back in the city. For those who don't know, I did my PhD like 20 meters down the road at the Astrophysics Research Institute. But yeah, today I wanted to talk to you about something a little more inclined on the data-driven aspects of science and some of the things that I've been thinking about on applying data-driven methods and machine learning-like methods to astronomy. And I'll be talking specifically about simple, or as I call them, dumb foundation models for astronomy. And hopefully I can convince you that we don't need complicated models to solve big questions. So first and foremost, before going into the science, I need to just quickly mention the team effort. So stuff that I'll show you today is in collaboration with a bunch of people from all over the world, really, but mainly in New York City, at the Flatiron Institute, and in Australia, in Canberra and in Melbourne. And these are the beautiful pictures that they put on their website, so I stole them. But what I'll be talking to you about today is foundation models and an example case with a model that we created called Lux. So I'll start off about talking about what foundation models are and refreshing you on why they're useful. I'll then talk about some examples of foundation models for astronomy, the science discipline that I care about, and specifically narrow down on the field that I research in, which is trying to understand the Milky Way galaxy, our own. And then I'll introduce Lux as an idea, and then where we are in terms of it in practice. By the way, since we're a small group, if you do have questions along the way, just shout out. Don't be scared of asking questions. So first off, what are foundation models? So, I mean, depending on who you talk to, there's many different ways of defining them, but I took two definitions from some recent papers. And so, for example, one by Bomasani et al. Describes a foundation model as any model that's trained on broad data that can be adapted to a wide range of downstream tasks. Another definition of foundation models is that they are trained on vast amounts of data and can be adapted to a wide range of tasks. So you can see that these two definitions, as well as many more that I'm sure people have told you over the years, have in common the fact that they're big models that train on a wide range of data. And the reason why they're called foundation models is because they can perform many downstream tasks or output tasks. So that's kind of what a foundation model is. And structurally, you can think of it as a model where you feed it a bunch of different data, typically different data modalities. So for example, text information like large language models, or you can feed it images, speech, videos, etc., etc. And then you create this sort of model in which you train on this data. And then once it's optimized and you're happy with that kind of model, you can use it for a wide range of adaptations and these downstream tasks. So for example, for prompt answering, so what ChatGPT does, or for information extraction, say you had a research paper and a large language model that takes that, digests it, and then spits out like a resume for you. These are the sort of kind of ideas that foundation models are developed for. And of course, as you can imagine, they can apply to a wide range of problems. Keep pressing the wrong computer. So why are foundation models so useful? The main reason, I think, is because they are extremely versatile. It's like having your own little personal assistant helping you answer a bunch of different questions and doing all the dirty work for you. But broadly, they're very useful for 5 different categories. And this, by the way, this was taken from that first paper that I showed you, that book, Bomasani et al. In 2022. So if you're interested in this, I'd really recommend reading that paper. But I think they can be, so foundation models can be broadly classified into 5 different groups. For example, language, and this really concerns large language models, LLMs, or natural language processing models. And these are basically essentially chatbots. So your ChatGPTs, your Claudes, DeepSeek, Gemini, whichever one you care about, which is a sort of model that you have you're basically talking to someone, right? You ask it something or you enter a prompt and it'll give you a reply by searching on the web and having been trained on thousands and thousands of documents. Another area is vision, and this involves image creators. So these are your models like DALL-E or BERT, and now ChatGPT as well, where you ask it a prompt and it will generate an image for you. And now we're seeing that it's being also developed for videos. So for example, you want a llama with a fancy party hat on, dressed in a bikini, and it'll create an image for you and spit it out. I think one of the areas that large foundation models are going to be very useful for is in robotics, and this involves robotic foundation models, which are trained on the combination of vision language models, and large language models for robotics, so for creating robots. For science in itself, foundation models are used for reasoning and search, so they're good at doing certain tasks, as I'll show you in a second, or for digesting resources. And lastly, there's also the type of interaction which involve foundation models like, for example, Siri with Apple, where it customizes your experience and it learns you basically, and it becomes your sort of a personal assistant that can answer any questions that you want. So for the actual sciences, you can imagine how these foundation models are extremely useful. So in bioinformatics, this has really taken off. So here's a plot from Guo et al. In 2025, where they summarize, it's this review article summarizing all the foundation models developed in this field. And you can see them classified into the different subtopics in bioinformatics. But as time has gone on and models have become better and computational abilities have also become better, you can see how many of these have been created for different tasks, right? And this is just exponentially increasing now. The same applies to chemistry, another field that's really data intensive and requires a lot of painful twiddling with models and theories, and foundation models are really useful for here. However, I'll be talking about how they're useful for astronomy, and different to other science disciplines. The reason why they're very popular in astronomy is because of two main reasons. One of them, data in astronomy is typically public, which is different to all other science disciplines. So for example, medicine, you can't just go to a hospital and ask for all the data collected on patients. You need to ask for permission. However, astronomy, we're very collaborative and we're very open source. So we share data as soon as we gather it, basically. This makes it very easy for people to then collect different types of data in big samples. And the other reason is because astronomical data is complex. It's very hard to model astronomical data, right? We're looking at the cosmos. It's not an easy thing to understand. So these sorts of foundation models are very attractive, trying to understand all these different data modalities in astronomy. So I'll just go now through some examples of foundation models and specific types of foundation models in astronomy and what they're being used for. So I think a couple of months ago, you had Joanna Chuka talking here, and she talked about Universe TBD, which is this sort of collaboration that's aiming to, make astronomy accessible. And one of the things that they're really developing is this large language model to help with the digestion and the research findings, basically, which I'll talk more here. So they have these different sort of sub-projects on this larger Universe TBD collaboration. And I flag this collaboration not only because Joanna's my friend, but also I think it's really a positive way of thinking about these models, right? You're not just using it to solve your problem, you're using it to actually promote science and make it easy for people who come from less privileged backgrounds actually access science. So one of the things that they're doing is this multi-modal universe where they're basically trying to collect all the amount of data from different telescopes and different surveys and different collaborations, and they're trying to put it all in one place to make it easily accessible for people. Another thing they're doing is this Pathfinder AI, which I found quite interesting because Joanna sent me a text saying, we've just looked at your paper with this and it's given a really good resume. And when I looked at it, it was actually really good. But it's this AI assistant that basically you throw a paper at it and it'll digest it in about 20 seconds and it'll spit out a really good resume with plots and stuff. So very useful, for example, for PhD students starting in a field, trying to understand what's going on. And the other thing they're trying to develop now is this AstroPT, which I don't really understand what it is, but it's a sort of large observation model, and it's developing this model to be able to understand, I think, telescopes and what the different properties of telescopes are, and how we can reduce all the data in a homogeneous way. So yeah, more on this Pathfinder if you're interested. This not only applies to astronomy, I think they've made this now to any research paper. So if you're interested in trying it out, give it a go, and you can find it at this link. Another example of these sorts of foundation models and large language models for astronomy is this Astrolama, which is also part of University of Edinburgh, but done by other people. And it's a similar principle where you have this model that can help you understand different research outputs, and kind of you can talk to it to help you with like your everyday queries and things like that. So instead of going to your supervisor and asking them, you know, those annoying questions, or not annoying questions, but like you wouldn't want to go to your supervisor every day, right? So what you can do is you can, I guess, ask this chatbot. Now, other foundation models that have been developed for astronomy on a more scientific level are things like this AstroClip, which, if you're not familiar with, is a foundation model that essentially takes data collected on galaxies. So they take galaxy images, and they take galaxy spectra, which are these crazy wiggly lines. And the idea is to create a model that has this embedding that can then create the data in itself. And the reason why this is interesting or important is because with the amount of data that we're now collecting from telescopes, we want to make a pipeline to make it quick and precise to be able to obtain the actual values that scientists care about. So going from the actual observation to the output and the catalog that people use to make science. And the reason why I flagged this AstroClip is because it's actually quite impressive. It can collect different types of data, so images and these one vector arrays, these spectral lines, and it can really precisely measure redshifts and the masses of galaxies, and other properties like morphology and classification and things like that. But you can see how this sort of model is collecting all these different types of data, it's learning it, and it's creating some relationship and correlations, and then it then spits out different data modalities or different properties that you care about, redshift, mass, etc. Similar to that one, there's been a bunch of others being put forward. There's this group called Polymathic, which is a collaboration based in New York, but has people all over the world. And they're really working on this, on creating these sorts of foundational models for science and astronomy, which I don't know if I agree with the concept itself, because the concept is based on the idea of creating one model that can rule it all and understand everything in science. But I think it's still an interesting problem to tackle, to create a model that can really understand everything that we're collecting from astronomy to then make these sorts of precise measurements and understand the cosmos. And one of the latest ones that's been developed is this Aeon 1, which is a really interesting read if you have time. Now, coming down to the Milky Way, so our own galaxy, there's been foundation models developed for this field as well. And one of those is this one I'm flagging here from Henry Long in 2023, which is a transformer-based model. And if you don't know what a transformer is, it's basically like a complicated neural network that has a bunch of layers. But it's arranged in a certain configuration that has been found to be very quickly optimized and very precise. But the basic idea is that you have a bunch of different data in the Milky Way. So you observe individual stars and you collect, for example, the amount of light, so the photometry, or you collect spectra. So you split the light by wavelength. You collect also information on the motions of stars. And then this one model collects all that information and it learns the relationships from it using this neural network. And it does this encoding. And then from that, you can understand the stars and obtain measurements of the properties of stars. Say, for example, how much iron that star has or how hot it shines and those kind of things. And this is extremely useful, right? Because you have a bunch of different surveys now in the Milky Way, observing thousands and millions of stars, each one with its own instrument and its own problems, and then determining their own set of measurements. So you can think a model like this would be able to combine all those measurements to create one overarching catalog, making it a lot easier for people from different surveys and different communities to actually move forward in science and compare their results. So something very useful, I think. But of course, to get to here, you need to create this sort of very complicated model. So this, being a transformer-based model, is based on this neural network approach, and you need to train it on a large number of layers of neurons, and it typically takes a lot of time and a lot of resources. As I was mentioning, for the Milky Way itself, this sort of idea of collecting all these different data sets and creating a model to homogenize everything is becoming very important. And this is because of the amount of vast and rich data that we're collecting. So if you are not in astronomy, you might have heard of this space mission called Gaia, but it's been revolutionary. Oh, someone's telling me to mute myself.
No, it's somebody in the audience needs to be muted.
Okay, cool. I'll just carry on. So if you're not in astronomy, Gaia is this space mission which has now been decommissioned actually, but we're still reducing its data because it's just collected that amount, like that crazy amount of data. So on the order of billions of stars now. And what it's doing is it's been really revolutionary in the sense that it's collected the motions of stars and the positions, as well as how bright those stars shine across vast regions of the galaxy, really allowing us to learn about the structure of our Milky Way system and learn a lot about its evolution history and galaxy formation as a whole. Now, in addition to that, there's also a spectrograph added to that survey that has collected also a bunch of data. And as I was mentioning, we're talking now in the millions and billions of stars, right? Now, if you combine this with all the efforts from all these other surveys that have been collecting data in their own way, we have this sort of view of the galaxy that is just marvelous. If you're a person like me that cares about the Milky Way, it's like the perfect time to be doing this kind of science because you just have endless amount of data, which is awesome, right? So this is allowing us to see the galaxy in all these crazy dimensions. So for example, we can really probe the chemical compositions of stars in the galaxy, so what the chemical DNA of stars, and this allows you to piece together the star formation history of the galaxy and how it evolved chemically. We look at the colors and magnitudes of stars, so how much light is emitted in a given bandpass by that star, allowing you to create these color magnitude diagrams, or the Hertzsprung-Russell diagram, and to segregate different stars and different stellar populations in the Milky Way. The precise measurements of the positions and motions of stars allow you to look at the kinematics and the structure of the galaxy. And we're now also piecing together a temporal aspect. So we've started to measure the ages of stars. So you can see how both the sheer quantity, but also the quality in terms of the different data modalities that we're collecting in the Milky Way is insane. And just as a refresher for people not in astronomy, the type of data that we're collecting comes in four main flavors. So as I was mentioning, Gaia was really good for the astrometry, so for measuring the positions and the motions of stars, which you can then understand their velocities and the kinematic structure of the galaxy or their orbits. The photometry gives you essentially how much light is emitted by a star in a given bandpass. And if you compare different bandpasses, you get a color, for which you get these beautiful color magnitude diagrams. The spectra, so if you shine light from a star through a spectrograph, it will split it across wavelength. And then these crazy wiggly lines give you a ton of information of the properties of that star. And this is the thing that I'm really excited about. And then more recently, there's been a lot of efforts on measuring the interior pulsations of stars, which is what we call astroseismology. And I'll just pause there because to think that we're looking at a star and we're seeing it pulsate and seeing the modes inside, to me is insane. But we can do that now. And the reason why that's interesting is because from that and the laws of stellar evolution, we can derive the masses and the ages of stars. Really useful quantities to measure. Now, with all this amount of data, I now want to introduce the model that we put together, which is called LUX. And I want to introduce this generative multi-output latent variable model for astronomical data with noisy labels. So that's the fancy title. But essentially what this tells you is it's telling you that it's a simple foundation model for astronomy. It's generative because it can create the data that you're inputting, so it learns a relationship to be able to replicate the data. It's multi-output because it has different downstream tasks. So it can perform operations to learn about parameters of stars, or it can do it to learn about spectra, or it can do it to learn about parallax, etc. And it's a latent variable because it has a set of variables that the model optimizes, which mean nothing, but when put together, output the properties that you care about. And at noisy levels because astronomy has noisy information to start with. So going back specifically to stellar spectra, as I was mentioning, so if you shine the light of a star through a spectrograph, it splits it across a wavelength, and then it creates these beautiful wiggles. And these wiggles give you information about how hot that star is, how compressed it is, and the density of it. But in given wavelength regimes, you can also measure the chemical composition of that star. So in other words, the chemical DNA. And this is extremely important because then you can piece together where stars were formed and how they evolved, etc., etc. Now, if you were a spectroscopist, what you would typically do is you would take your data and you do your reductions and whatever, and then you'd get your beautiful spectra. You'd then go to stellar evolution and you would create a set of models and this grid of synthetic spectra to compare to. And then you choose your best comparison technique to be able to map the observables to the models. And then from that, you would infer some parameters of that star, give it its how fast it's rotating, how hot it's burning, what it's made of, its age, etc., etc. Now, this process is reliable. We know it works because this is physics, but it's very time-consuming, right? It takes a lot of time to first reduce all this data, then compare it against that, develop these models, compare it against the models, etc., etc. So for the vast amount of data we now have, billions of stars, this becomes very time-consuming. A new way of dealing with this is if you already have people who have done the groundwork and have got these parameters for you, but you have new data, you have new spectra, you can create a model that understands the relationship between the spectra and those parameters for a subset that you train on. And then if you get more spectra, you can just create a model that can directly map to the parameters. And the beauty about this is that you get stellar labels much more quickly, but also if it's generative, you can also predict stellar spectra. So you can compare what your model is doing, but in both directions, right? Multi-output. And the advantages of this is that it's typically much faster and computationally much less expensive. The other advantage is that when we do the traditional modeling, you typically take windows in the wavelength regime of the spectra of stars. And this is good because you're focusing on a given region that you care about, but it's bad because you're throwing out a bunch of data, right? You're throwing out the rest of the array. But these models are trained on the full spectrum, which means that it captures all the information in that spectrum. More information means you can learn more about the star. And this is why these models are shown to yield more precise stellar parameters when performing these sort of comparisons. So there's been a lot of work in astronomy trying to develop these sorts of models, and they range in complexity. I think the initial one was called the Canon, which was by Melissa, one of the people that I initially introduced, hence why I work with her. But it's this sort of idea that you can create a simple linear model to learn about these parameters. And when I say a linear model, like it doesn't involve creating a neural net or anything like that. Like a simple linear model can actually replicate the data very, very well. But of course, with the development of more complex models and neural networks and so on, people have also used these and have shown that these are really useful as well. So there's been a bunch of different ones. However, all these models, when they train on the data, they assume that the parameters that they use in the training set are God-given. And by this, I mean that they have no uncertainties. But if you have ever looked at data from a star, you will know, as anything in physics, right, that that data has uncertainties. So this causes some limitations. It causes limitations when training the data because you have to throw out a bunch of data that's not certain. It also makes you throw out a bunch of data because say if you had observations of 100 stars that have 10 parameters, sometimes you're going to get 100 stars, but not for every 100 stars you're going to get the 10 parameters. You might get for a subset of those 10 parameters, but for like 70% of them, you might only get 7. But if you're training a model to predict all 10 parameters, you need to throw out those that don't have all 10 parameters measured. This becomes very wasteful because you want to essentially create a model that can incorporate all the data at once, right? And therefore, this sort of limitation can lead to biases, or it can lead to the ability to perform label transfer. By label transfer, I mean take the mapping from one telescope and the parameters observed in one telescope and project it onto stars that are observed with another telescope. So this is where Lux comes in. And the reason why we built this was to perform label transfer and to make it a bit more flexible when compared to these previous models. So I think the main advances of Lux versus previous models is that it can deal with stellar label uncertainties and the parameters that you input it in the training data. So it takes this into account directly in the likelihood function. So it means that you can throw any sort of data at this, uncertain, not measured, partial labels, whatever, and it'll still work. Because it can deal with uncertainties, it means that it can deal with partially missing labels, and I think this is the main advantage. So again, if you have 100 stars and only 50 of those have the 10 parameters and the other 50 only have 3, you can still train on the 100 stars, and the model will still be able to predict those 10 parameters for all those 100 stars. Whereas before, you'd have to reduce the amount of training. It's written in JAX, which is this latest machine learning software by Google. So it can do auto differentiation very fast. And the beauty about this model is that it's dumb. It's a linear model. So it learns these relationships by just using a linear model within the latent variables. So the structure of Lux, the simplest form is this one here. So if you've never seen graphical models before, this is a representation of Lux as a graphical model. So here, L is labels or parameters of a star. F is flux, so your data, your spectra. And then these things are latent parameters, so numbers that don't mean anything, but we optimize to then be able to predict these things. And then the uncertainties and some extra scatter in case you don't trust your uncertainties on your input data. So you can see here how the model is divided into different plates. So you have the parameters plate, right? You have the flux plate or the spectra plate, and then you have one that connects both. So the model, the way it works is you optimize these 3 things. And then once you have those 3 things, if you have more flux, you can get these with those to then predict labels. And if you have labels, you can go back the other way. So you can see how it's multimodal and how it can do many different downstream tasks. The weird thing is, compared to like the neural networks and things like that have an encoding process and a decoding process, this model actually doesn't have that. This just has a decoding process. So you learn these on the fly. Which is an interesting property if you care about the sort of structure of models. But you can see how this will be useful if you then expand this and you add different data modalities to create this sort of dumb foundation model for Milky Way science. You have this model in the middle that connects to all these different data modalities, and you just keep throwing in different plates, one for spectra, one for astrometry, one for photometry, and one for astroseismology, and then it has a model that can spit out all these different properties of stars depending on what you feed it. Now this, I think, will be extremely useful for the deluge of data that we're going to get. So we have an insane amount already, but it's going to become even like 2 or 3 times as much in the next few years. And this is thanks to next phases of Gaia, but also all these different surveys that are coming online, which will allow us to see Milky Way in this grandiose picture. And I think Lux will be really good for constructing this sort of homogeneous catalog. So the thing I'm really excited about this is to use it to perform label transfer or take properties from one survey or one telescope and project it to stars observed in a different telescope. And the beauty about this is that you can then create a catalog that's homogeneous. And this is extremely important because at the moment, people are like taking their own data from their own telescope, claiming something, but you can't compare apples to apples with other results. You always have to have like a hand-wavy argument. This will allow you to actually compare apples to apples. And then you can say A is better than B, or B is better than C, or C is worse than B, like anything like that, okay? So this is the concept. Where are we in the practice? So I only started working on this year. So we only put this out recently, but we've done decent so far. So at the moment, Lux is specifically designed for dealing with spectra or flux from stars. And this is a sort of foundation model, as I said before. And we've tested it on different surveys. So here I'm showing you results on giant stars in the Milky Way observed with this apogee survey. And here in the background, I mean, it's hard to see, I apologize for that. But the black line gives you the actual observation of the telescope. And then in blue, you have the prediction from lux. And because of the way lux is structured, you can predict the flux from both labels and fluxes. But ignore that. The point is that we have the model flux and we have the real flux. And you can see that the model does very well compared to stars ranging in different properties, right? And the cool thing is that where there's failure modes in the observations, because of uncertainties and how telescopes operate and not being able to observe perfectly, the model can repair that stellar spectra and can actually give you a more precise spectrum for that star than the actual data. And this is because it learns about that star. This is very, very helpful. When in terms of the actual parameters, here's a comparison using stars from Apogee again, and the parameters determined with our model, the ones determined with the previous model, and then the ones determined with the actual pipeline in the survey using the initial traditional spectroscopic way. And you can see that the labels are very similar. However, there's some small differences. If you look, for example, at these stars here, you can see how it changes, right? Here, there's a hard cutoff, and there's like weird overdensities and things like that. It becomes a bit smoother in this model. But you can see how it's like very smooth and very like a nice gradient, which is what you would expect in this plane with the uncertainties model. The same applies to the metal poor end, so this end of the diagram, for stars in the Milky Way. There's a distribution here, but the scatter is quite large, and then it becomes more certain, and you can see how stars with different orbits congregate in different blobs in chemical space. And it really is able to reduce the scatter of the model and really pick out stars formed in different environments. Which if you're someone like myself or Anna or anybody else that's trying to find things in the Milky Way, then this becomes really useful because that is much easier to find than that over there, right? Here's another example, which is telling you the same thing. The scatter is much smaller compared to previous models or the actual reduction pipeline, allowing you to identify different clumps. Now, that was the emulation sort of results, so how the model compares to the pipeline. But as I was mentioning, the main advantage of these sorts of models is the ability to cross-match different telescopes and obtain parameters from one telescope for stars observed in another one. And here's an example obtaining parameters for stars observed in Galar and Apogee, 2 different surveys. And this is just 5 different chemical planes. So just parameters of stars that were determined with our model and then the actual survey. This weird line here corresponds to stars that didn't have a measurement in the actual survey, and this is because of uncertainties or whatever problem with the reduction pipeline. Our model still is able to recover that, and this is because we can incorporate uncertainties in the training data. So the model replicates well the distribution, right? And it even leads to a smaller scatter. But the cool thing is, which I still don't really fully comprehend, is that this element, and this element should not be able to be, you can't deduce that, that information from Apogee spectra. But yet this model does that. So it's learning something in there, something we either don't know or some correlation that we don't understand. And it's still able to infer these parameters for these stars. So quite powerful. Here's another example showing how we did the same thing. We did label transfer between the 2 different surveys. So in this case, Apogee and Boss. And different to the previous result, in this case, we're comparing 2 different surveys of different resolutions. So Apogee is a very much higher resolution, which means it's more certain data. Boss, on the other hand, is much lower resolution, much less certain data. But even with less certain spectra, we can still learn the parameters that you would get with higher signal to noise and better data. This will be extremely useful, and this is more for the astronomers, I apologize, but this will be extremely useful for looking at the twin galaxies that are around the Milky Way as we speak, this large and small Magellanic Cloud. So if you've ever been in the southern hemisphere and looked up in the sky at night, you might have seen 2 weird blobs. Those correspond to these 2 galaxies. And with this survey BOSS, we're really collecting a large amount of data. So you can think of how this will be really useful, right? If you have a bunch of data with Apogee, but there's much less stars, you can create a mapping for the parameters of these to all these stars to then get the parameters that you care about for a much larger sample. And this is something that I'm currently doing. So just to wrap up here, the new and more data require new and better models. I think we should, the more data we're collecting now and in all realms of science and life, it require us to create better models to understand it. However, just because we have these crazy complex models that do really fancy things doesn't necessarily mean that we should use them for every single task. And this is the sort of message behind Lux. It is a very simple, it's the simplest model you can get. It's a linear model, right? However, it can still really perform really well and it's very powerful. And here I'm showing you how this simple or dumb foundation model can do all these different things. It can do emulation tasks, it can do classification tasks, and it can do this multi-survey translation or label transfer task. My aim is to develop Lux to become more flexible. I think with more data, say for example, more complex data like astroseismology or other sorts of astronomical data, we might need to go beyond linear. So I think having a framework that's interchangeable and you can throw in a linear model if you want, or a quadratic, or a Gaussian process, or a neural net, or whatever, will be useful. I'd also like to make this probabilistic, to make it a more Bayesian model. And I think all this is building towards it being a foundation model, basically. And my ultimate aim, or my immediate aim, is to perform label transfer between all these different surveys to create this sort of homogeneous map of the galaxy to then give to people and let them do all the science that they care about. So I might have gone a bit quick there, but I'll just wrap up and I'll thank you.
Okay, I'm gonna figure out how to get the kind of volume kind of working out. But in the short term, does anybody in the room have any questions for Danny?
Yeah, in terms of structure of how Lux is set out as a neural network. So I'm familiar with transformers that have encoders and decoders. You say it learns on the fly, so it's no need for an encoder. Is every individual task like an individual decoder?
Yeah, exactly. So here, for example, I don't know what I did. So just click there. So here, for example, this process is one decoder, and this process is one decoder. But there's no, like, the data's all in the decoding process. This is the data. So you train it, and then if you have more of this, then you can do the decoding process. So it's a weird concept, right? Because in neural networks and the standard transformer models, you would have data up here. You have an entry point, which is your encoding process. You would learn a latent space, and then you would project out of that. This is weird because it learns from the data itself whilst it's also optimizing and spitting out what you want.
So it's so is there here a like a sample, like is that stochastic variable in package?
It's random, yeah, it's a random variable. So these things are completely, like, the numbers don't mean anything, essentially. And so the way it's designed is that this matrix will have a certain dimension that matches the amount of labels and the amount of latent dimensionality. And that's one parameter you can vary. You can make it more complex or less by varying the size of that array. The B does the same thing, but with the spectra. And then this one is like, you can think of it as like a latent that corresponds to every star or every point. In this case, they're stars, but it could be galaxies, or it could be, I don't know, measurements of like the brain, right? It could be anything. And then once you have that, these two combined give you labels, these two combined give you flux, but you can think of it as like another thing, and another two will give you something else.
Sorry, last one.
Yeah, no,
so if I have lots of flux data and I want to generate the other one,
yeah.
then the distribution of Z will depend on the flux data. And then
yeah, well, these depend on both because it connects to both. So when you train it, it speaks to both.
Oh, and then by the actual training, A, Z, and B are all tuned. And
exactly. So once you've trained it using both, you get all three, and then you can think of it as, right, okay, these are the things I want, but I have this. I'll get more of these, and then I'll get these to then project back onto here, and I'll get labels. But it's a good question because it's not a common thing to just have decoders and no encoders. It's a weird,
it's interesting.
It's a weird setup.
I've got a weird transformer that I'm looking at.
Okay, so I can see that Ryan online has raised his hand.
Actually,
Okay, if I speak out, Ryan, we'll see if the audio is working in here. Okay.
Yeah, can you hear me?
Yeah.
Is that all right? Is that clear? I'm gonna assume, yeah, sorry, I can't really hear you guys.
Yes.
Yeah, okay, nice. So I was gonna just to clarify, is this trained on current observational surveys? That's the training set, right?
Yes, so we tested it on both theoretical spectra and observed spectra. So it works on
Yeah.
Yeah.
Yeah, so I was just gonna ask, do you see any like issues? Do you think you'll have to retrain the model for future surveys? Because there may be potentially some issues with like domain shift if you've got, I'm not an observer, but if you've got different telescopes looking at different things with different quality, different mission objectives, would the model need to be retrained each time you incorporate like, if you wanted to look at a survey that it hadn't been trained on, do you think it would struggle or do you think it'd be okay?
It's a great, I mean, this is exactly why we built this model. So it depends what your end goal is. If you had, say, 100 stars and you have observed it with one survey and you've trained a model to be able to predict those properties, you could have that model. Now you observe it with a different survey, but you want the properties to be painted onto that one. You could either add a plate, and then that means the foundation model is growing, right? Or you could just scrap this all together and just create a separate model to train that. It depends what your user case is. If you want to start building a framework that will just be one that can master it all, you just add on to the one you've already built and you've already trained on. You would have to train a set, like every time you train in a decoding aspect. So if you had another plate here with a different survey, you'd have to train these later. These will still be the same, but the new ones you'll have to train, right? Because the model needs to learn what the new data is. But once you've done that, you will still have these, and then you'll have the additional ones. Does that make sense?
Yeah, cool.
Yeah.
And then, sorry, if someone else, yeah, that's fine. Someone else can go first, sorry.
I had a question like sort of relates to that. So I guess my question was going to be how scalable is this, which I think you've just answered with Ryan. Do you envisage allowing a user to sort of choose what the training data is? Like, so I can imagine like a kind of like a jigsaw kind of GUI type thing, where you say like, yeah, I don't really like Apogee for whatever reason, but I'd really like to include these things. So I guess part of that is how easy is it to train? Like, do you have to have specialist computing facilities? And secondly, like how sort of modular is this?
Great question. No is the answer. Right now, because it's so simple, all the results I showed you were trained in 10 minutes on my own laptop, which is 2 CPUs. Right. So like this is super quick. So the idea is, I mean, you can think of it in 2 ways. I would happily create a model trained and put that online for people to use that they care about. But what I want to do is create an infrastructure that then people can take and make it with their own. Because at the same time that you can add different plates here for different purposes and different data, you can also think of it as like this decoding aspect right now. I've assumed it to be linear, but people might not want it to be linear. Yeah. People might want a neural network, or they might want something else. So the idea is to create a code base or like an infrastructure that then they can take and say like, right, I have this data and I want this result. What's the best thing for that? A neural network. And all they need to do is just call in the Python function neural network instead of linear, right? And that will just work for them. That's the kind of idea, which I guess will make it easier to become scalable. This needs a lot more testing first, though, right? Like we're nowhere near that stage, but that's the ultimate goal.
Yeah, very interesting. Okay. Yeah, David.
Roughly, sort of how many parameters are there in the A, Z, and B sections? Because often with large neural nets, you know that it's doing something, but you don't really know which bits of the net are doing anything in particular.
Yeah.
And you can sort of knock bits out and maybe guess that way. So just curious as to how many internal parameters your models have.
Cool. The results I showed you, just to be specific in this example, the M, which is your labels, is 14. The wavelength is 8,500, and the N is 5,000. Sorry, the Z is 5,000. Now, that obviously can change in whatever you want, but each of these are matrices, right? So the one parameter that this model needs is to set the latent dimensionality, i.e. how many random variables do you want to fit for each thing? And that's where you learn about the actual data. So for example, if you set that to be very small, say you set it to 14, And I would imagine that what the model will do is it'll say each parameter will connect to one of those latents, or there'll be like weird combinations of those. If you set the latent dimensionality to be like 5 times the size of the labels, for example, it's probably going to work with the necessary first X amount, probably like 14 to 20, and then the rest will just be like very small numbers that capture like irregularities with the data, or errors that are propagated from systematics in the telescope and things like that. But it's a very interesting problem because I think you will actually learn about the data that you're collecting and the telescope and the instrument that you're using as well.
I was just thinking, I was sort of long time, I'm a high geophysicist, spent a lot of time looking at inverting matrices and so on, and the sort of noise in that.
Yeah.
So if you can make your linear thing, it's effectively, as you say, just a matrix. If you could make it invertible, then you can actually say, the thing that says that this star is of this type is these parameters. You can actually work out the relative weights, the relative, the correlations and anti-correlations. But I'm sort of not seeing that you can do that directly from your model, but maybe I'm missing something.
I think so. The way this works, by solving least squares, it does. So you could do that, I think, but that's only because it's linear at the moment. As soon as you go for non-linear, obviously, as you know, that won't work. But the problem is that it depends on, and in our case, it depends on the dimensionality of your latent space, I think. Because the bigger you go, then there'll be latents in that array that learn things that are not really useful, right? And then it could spit out something. But
I did sort of inverting matrices as a generically.
it's a hard problem.
I was wondering, I think you've got enough parameters that it's not going to be possible for the way you're doing it. But that was why I was just.
Yeah.
Okay, thank you.
So we've got a question in the chat. Sound like a Twitch streamer. Is there any way of using models like this to create data relating to like unseen matter, like dark matter, based on the kind of visible matter that you do have access to? So I mean, I guess you have to collaborate with Ryan on this and bring in simulations. But could you imagine like some of the data that you're kind of generating be like dark matter structure, densities, whatever?
I think it's an interesting question. I think maybe, I mean, you have to resolve to simulations, right? Because there's no other way, I guess, of relating visible matter to what we know about dark matter, right? Unless you do use simulations. So the model will learn some relation in that process, and it will spit something out that might be sensible. I think the thing I would be worried about is that it's learning about that simulation and the laws that you've inputted to that simulation, rather than actually learning the relationship between visible and dark matter, if you know what I mean.
Yeah.
So I guess it's how much you trust the mapping from your simulation to the real world would be the thing that I would
yeah, I always thought there's something to do with like symbolic regression here, because you could do something like I've got my point particles kind of moving around.
Yep.
What model of physics sort of gives me out the best solution for what's going on there? So either it gives you some kind of really tricky version of modified gravity, or you give it the space to say that there's something else there, and maybe that tells you something. I don't know how much more useful that actually would be than just direct measurements.
I can't see the direct link with this specifically. I think one way you could approach it is you create a mapping. So, for example, instead of labels and fluxes, you had properties of dark matter and properties of visible matter, and you go to a simulation, you do the symbolic regression idea, and you create a mapping that projects one to the other. That's great. You've learned about that mapping in that simulation. And then I guess what you could do is inspect the latents and try to understand if there's a relationship between them and how that relates, for example, to the laws of physics. But I don't know how easy or how feasible that is. I think because you're learning about the setup in the simulation at the end of the day and what you inputted, right? So
I suppose you have to go back to the kinematics, wouldn't you? Like, is there something going on that your first order understanding of how gravity works can't explain? Like, you look at stellar clusters, you look at the Magellanic Clouds, you look at inner Milky Way, outer Milky Way. Yeah, I don't know. It's just a separate question, I guess.
Yeah, there's a lot of people doing this, and they throw like these big graphical models at these sorts of problems, and they learn like the relationship in the structure of the data, so like the physical positions and how matter is distributed, which I think correlates a lot more with dark matter problems. There's also people that try and infer the laws of dynamics in a data-driven way, and I know that sounds weird, but they're learning actually like to derive the Jeans equations or like fluid dynamics and things like this. maybe you could approach it in that sense, but like again, I think the main issue for me would be that you're learning about what you've inputted to that simulation because you're not observing the real world. I don't know how you then map that to. You could learn something obviously, but I don't know if you're learning about that simulation and what you've inputted it, or you've actually learning from about the real world.
Yeah, interesting. I hope that answered your question, Pritam. So I guess next we can go back to Ryan online.
Yeah, cool. So I'd said a separate question. So you showed that plot, well, it was a set of plots. So it was the stellar spectra and it was the lux. Yeah, exactly this one. So this is really cool. And we've seen like, especially larger models like AstroPT can do similar things where it can fill in the gaps where you're missing data. How did you actually verify? I'm sorry if I missed it, but how did you actually verify that it was accurately, predicting the gaps in between if it's just missing data entirely? If that makes sense.
So how did I actually? So there's the numbers way, right? Like we did the whole cross validation and chi-squared metrics and all that kind of thing. But I think what I did was I took doppelganger stars, and by that I mean two stars with similar properties. One will have a thing like this, like an aberration or an error in this flux, and the other one doesn't. And then I predicted the flux for both of them, and then I compared them. And then I compared the one that actually doesn't have it to the one that does, and they look reasonable. But that's as far as I got. I don't know that way, but I was happy with that.
It's really interesting that it works like this from
it's bonkers, right?
fairly,
it's nuts because like these wiggles are hard, man, and like stars are not easy. So like the fact that a linear model matches it's crazy. But
yeah. And then just like a follow-up point, this isn't a question, but from what David was asking, I don't know if you've looked at John Wu's papers on sparse autoencoders, but that seems like a really cool way of like, it basically takes the top activating features of a neural network. I think he used like a CNN. And from that, you can actually linearly combine the top activating features to see how it's making its predictions. So it's kind of, if you've got a really complicated high latent space model, you can kind of simplify it into something that looks fairly interpretable. But I don't know if that's what you focused on, but
I think that's very cool, by the way. But does that not tell you that your model's simpler than what you think it is, though? Like, does that not tell you that you don't need those crazy big models?
Yeah, exactly. Yeah, because I think if they took like the top 4 activating features or something, and it still had 92% representation of the whole, it was still extremely accurate, basically.
Yeah, that's the idea of a transformer model, right? You have this sort of big neural network and you have activation features that then tell you what to use of those latent variables to predict all the different properties, right? But then that to me seems like you're catching everything with a big umbrella instead of like learning the actual thing that you need to learn, right? It's very useful it's an easy way of dealing with the problem, I think it is. And it works and that's great. But I'm more interested in like trying to actually figure out how complex is the problem to start with. Yeah, but I'll check it out. I think I've seen it, but I can't remember off the top of my head that paper. But I'll look at it. Thanks.
Yeah, thank you very much for the talk.
All I was going to say was, as a suggestion, what you could do is just artificially knock out sections of your spectrum.
Yeah.
So just deliberately mask them and then give it to the model and see if it reproduces it, because then you've got a one-for-one comparison of what it was and whether it's it's just putting in some completely different stars version of the spectrum, which is visually okay, but not 100% statistically okay.
That's a good point. I should do that.
My follow-on from that was going to be, so is that your general approach to missing data? So if you have like missing labels as well as missing spectra, would it be to find, like you said, a doppelganger and do some kind of mapping and maybe inflate the uncertainty associated with that in some kind of way?
Yeah, kind of. So instead of finding a doppelganger, what we do is we just throw in the median of the distribution as that value, and I inflate the uncertainty to like a crazy number, which then means in the loss function it doesn't weigh anything. So it doesn't really count towards whatever it's doing. But that'll only be in whatever parameter that's not measured. Because you could still use that star if it had a precise measurement of some other parameter. You know what I mean? So you're not fully discarding it, you're just discarding it for that particular thing, that particular feature. Now, I don't know if that's the best way of dealing with this, because if you throw in a median or a mean, then what that does is it tells the model to like converge to the mean, right?
Yeah.
A median whenever it's not right or not there, which then can lead to like weird, like it's tending towards a mean all the time.
Yeah, so
You know what I mean?
maybe you should do like a random sampling from the underlying data to
Could
to
do.
that point.
So the thing I'm thinking of is to in the training step include a theoretical aspect to this, and that would be like your perfect model.
Yeah.
And then have like a loss function that incorporates both. And then in a case where you don't have a measurement, you resort to the perfect model and find like a doppelganger star with the perfect spectra and the perfect parameter space and use that instead.
Yeah.
And then that will not make it tend towards a mean. And it would also, because there's a lot of problems with like assumptions of the grid that you use and all that kind of thing, right? Which everybody bypasses. It's all dark magic. So like, it's how much, like how honest you are with the dark magic.
Yeah, sure. Do you have any other questions from the room?
Yeah, just following up from what you were just saying there. When you said that apogee you can't because the lovely at the apogee, yeah. So some of the elements you said that Gala can't deduce, and then your model can. Is it using that sort of like the perfect theoretical model to sort of?
No, this is.
How did it come to that conclusion?
Yeah, so just to recap, these are two surveys, the same stars, but this one's observed in the visible wavelength regime, and this one's in the near infrared. And just when you do these things, if you want to predict these abundances, you take a window, given some line list of people in labs, and then you use that window to predict the amount of abundance. Now, in the near infrared, which is the spectra I feed to this model, this abundance, and this abundance doesn't exist. But then it still learns a mapping somehow because Galar does have it. So the question then becomes like, is this because of a correlation or causation, right? And I think introducing the theoretical aspect would be really useful because then you could say, like, no, actually, it's not correlation, it's causation in the model process, right? But I don't know how else you would go about that. I think it's a common problem, but yeah.
Yeah, can I ask on the cluster thing? You mentioned about that it tends to cluster more tightly, which is you'd expect, but how do you know that it's right, if that makes sense? Like it's appealing that it makes a more natural looking cluster, but how do you know it? You're not just getting something that looks better but is actually like wrong or yeah.
Okay, so I guess double-headed question. So I guess I learned first, before doing all these plots, I do this validation, right? The same thing that any data-driven or machine learning model does. And I guess my confidence comes from asserting that the data that I'm using for my training aspect and my validation is reliable. Then if my model spits out values that match that, but are just slightly better, then I am confident that that is spitting out good information. And that's, I think, the reason why it leads to smaller scatter is because, again, you're training on the full data set instead of small regions of that, which is what these traditional recipes do. And I think that's why you get lower scatter. Now, having said that, there is an aspect of, is it learning correlations or is it learning causation? And I think if you know that, for example, the spectra that you're feeding it does have windows where these elements should predict, you can then look at derivatives, or you could look at comparing two stars with similar properties, but one abundance that's different, and then look in regions of the spectra where you'd expect it to change and see if the model's actually learning that. And we did that. And it seems to be working. But for the ones that obviously you can't predict because you don't know if there's any lines there or not, it's almost impossible. So I think a good, interesting problem is to actually go to these results and then look at the derivatives of the spectra and see if there are regions of the spectrum where you wouldn't expect it to change that are changing, and are you finding new lines, basically? But that would answer your question. My feeling is that for most of these, it's learning correlation, it's not learning causation, but I'm not 100% sure.
Cool. I think we'll finish it there. We're just coming up to the hour exactly. So we'll thank Danny one more time.
Thank you.
So we'll be back next month with another in-person seminar. This is from Andrea Santamaria Garcia, one of our new lecturers in the Accelerated Physics group. She's going to be talking about autonomous control of accelerators using reinforcement learning. So finally leaving astronomy for a bit. So yeah, hope to see you all again in person next month.